Hello again, I'm Dmitry Kulik, and this is the second part of our new short tutorial on functionality introduced in CemGEMS web application release 0.7.0 at the beginning of April 2022. So in the first part, we have reached this state, which you can see here on the screen. So we have created a recipe of sulfate-rich Portland cement, calculated its partially equilibrated state, which you can compare on the horizontal bar chart with the initial state, where we only had cement and water. Now we see some hydrated phases have formed, and the details can be found by expanding this equilibration results table. Here. This is equilibrated part, and this is the residual part, which consists only of this single entity cement material. And we also have created a process of type ingress by adding salt, which actually consists of carbon dioxide, as set in the process template. So we, in fact, simulated carbonation of this sulfate-rich cement. This produced a plot, a diagram, where we can see that upon addition of CO2, we consume portlandite here and produce calcite. And the overall volume and mass of the system increases because of addition of carbon dioxide. But looking at this plot, we already see that it's possible to go far more than 10 grams addition of CO2 to 100 grams cement to see more profound changes, more extreme degree of carbonation in this cement. And this we can now easily do by using the newly introduced widget called Process Settings Table. So if you click on this Process Settings Table, you can see that it consists of a main row for the whole process with time iterators that are now inactivated because they are all set to zeros. We will have a look later on how they work. And then two subtables. One is, so you can click like this to open or close the subtables. One is called spans and the other is called params. The params subtable is used for built-in cement hydration models, which we will consider in the next part of this tutorial. Now we focus on spans, and here you see 3 spans, and each of them sets a certain change of certain input in the recipe, stepwise by given number of steps, in this case 101. So we see that the first span, which is called adding salt, and as we know, in fact, it adds CO2, has this target path, we will come back to it later, and then it changes the addition of CO2 in a linear way from 0 to 10 grams with the step of 0.1 gram. The other 2 spans are still inactive because their step values are set to zeros. So in order to go much more deep in cement degradation by adding carbon dioxide, we can change this stop value in the first span from 10 grams to, say, 26 grams. Just type in 26. And then, because we don't want to calculate the step, we can simply type auto. And the program will calculate this step upon runtime such that there would be 101 steps. So after doing this change, we click on simulate process and wait what comes out. Now the process has been calculated. We can now explore the plot. And what we see is indeed we have gone much further in the degradation. So we basically have consumed all the portlandite and we produced a lot of calcite. We also have consumed siliceous hydrogarnet. We have consumed a lot of CSH, and we started producing some stradlingite and some hydrospheric oxide. So we see that there is a lot of changes in the phase assemblage in hydrated cement, potentially to occur upon significant reaction with carbon dioxide. And this case is a qualitative picture of more or less what's going to happen to cement by carbonation on air, where we have indiffusion of carbon dioxide into cement, but nothing effectively diffuses out, or practically nothing. We can have a different case, for example, when cement is immersed in water, in lake water, or river water, or even sea water, because in that case there will be indiffusion of CO2 into cement and out diffusion of some cations that are present in cement in much higher concentration than in water. First of all, calcium ions. So we can simulate this calcium output, so to say, or removal in a qualitative way without considering any reactive transport diffusion model by effectively removing calcium oxide along with addition of carbon dioxide. So we can do this very easily using this process settings table, expand it again to see spans like this, and then we see the second entry, which is called removing CaO. The idea of this entry is to control the amount of calcium oxide in a formula attached to the recipe directly. And now we can set up the same kind of change for calcium oxide, but with a negative sign. That means we will be adding carbon dioxide and removing calcium oxide. So we set this span from 0 to minus 26 grams, again with the stepping auto, and then we will achieve this effect, qualitative effect at least. So after we have changed these settings, we can click on simulate process again and see what comes out. And this is what comes out. So we can see that we have now gone in, again much farther in this process of combined carbonation and removal of calcium from our cement. And we not only consumed all the portlandite and even all the CSH, we already consumed stratlingite, but we also started producing amorphous silica out of CSH and some other funny phases like gypsum, probably some MSH, magnesium silicate hydrate, and so on. And we see that we still run at constant reaction extent or degree of reaction of this clinker, which is set in the recipe template to 28 days, and which probably is not very realistic for long-term cement degradation. So if you switch volumes to masses, you will see that the mass now remains constant, the mass of the whole system, because we effectively do not change the total mass. We add as much carbon dioxide as we remove CO2. So now we can ask what we can do if we want also to control the reaction extent of cement degradation. That means the reaction extent for cement itself. We can go back again into this process setting table and have a look at the third span called controlling react extent. So it was set like in the template to 0.835, which means that about 84% of cement should react and the rest remains as inert residual. So now we want to change it to some kind of progressive reaction, say to react extent 0.99, and then again tell it auto to see what comes out. And then we click on simulate process again. After 10-12 seconds, we can watch the result. So what we see now, indeed, that the cement is progressively reacting more and more, as we see here, this gray area, which is cement, silicate-rich cement, as the whole, as the material. And we see that, of course, this extends to some extent the lifetime of CSH, because we kind of produce more of it upon reaction. We need more carbon dioxide to convert calcium from CSH into calcite. So we see some changes that kind of would occur more probably when our cement can react progressively. Well, so now you have an idea how these things are controlled in the span subtable of the process setting table. But the question here is, what happens if I need one more span and I don't have it here? And for that we have this JSON editor, which can be activated with this pencil here. And it allows us to duplicate or remove entries in spans or params tables. So if I click here on JSON Editor and then expand the JSON document, then I can scroll it down and see that we indeed have this list of input spans, and all these three entries in the spans subtable can be found here. So this is the first one, adding salt, the second one removing CaO, and so on. Now we can make a duplicated entry using this menu on the left side. So we just choose an entry in the list and then click on the menu, and this menu contains duplicate or remove options. So remove is clear. Duplicate will just make a copy of that element in the list that we wanted to duplicate. Now we can close this JSON editor, go back to process settings table, and we see indeed that we have created one more entry. So suppose we want to change temperature with this additional span. So we give it a name, temperature, and then we give it like let it take the temperature from the recipe and let it go. Say we assume that the temperature in the recipe is about 20 centigrade, so let it increase to 40, and then it will calculate the step itself. But then the question remains, how do we set up the target path so that it would point on temperature in the input recipe instead of this amount of calcium oxide in the formula? And for that, we have here a very convenient and simple way to handle such things. We simply need to double-click on the respective cell in the target path column. So I just make a mouse double-click. You see that the colors, background colors, have changed. That means that I'm now focused on this target path for temperature. Now I have to scroll up to the input recipe and expand it and look where do I have this temperature. So actually, in the input recipe, temperature sits in this upper row. It's called temp here in centigrade. So to use the path, to create the path to this cell so that the process could change it stepwise, I simply double click on it again. You see the background colors disappeared. So they were appearing because they indicated which cells could be potentially changed by a target path from the process. So now we go back and see that again the content of this target path field has changed. Now we chose to recipe 0 temperature, the cell that we have now selected. And then we can basically click on simulate process again and run and see if there is some effect. So the process has been calculated now, and this time we don't see very significant effect because the phase assemblage changed only slightly, and the effect of 20 degrees change in temperature is not so dramatic in this case to see some profound changes. But the changes can still be seen if we would have exported the previous plot, like here with this button, export to PNG, which has also been added in this release. So we effectively click on export to PNG, and you see that it has saved the file, PNG file, to downloads folder. So, and then there you can go to this downloads folder on your computer and open this graphic file, which will show you exactly the same picture as you see here. So that's basically what I wanted to show you in this second part of our tutorial for release 0.7.0. In the next part, we will consider what to do and how to handle hydration models and the newly introduced params subtable. So, bye and see you in the third part.